So today we shall start a topic called characterization tools. Before that, we have covered non-uniform cell automata, and we have said that non-uniform cell automata, particularly developed under finite setting, right? Almost all cases, the grid or lattice size is considered as finite. Okay, so in case of non-uniform cell automata, some characterization tools have been developed. These are developed to understand the behavior, that is, dynamical behavior of non-uniform cell automata. Recall that all we have studied till now, most of the cases, they are the cell automata, classical cell automata. By cell automata, we always mean the classical one, where grid size is infinite and all the cells follow same rule to update their states. However, in case of non-uniform cell automata, we have a grid or a lattice where cells are allowed to use different rules to update their states. Okay, so we were particularly discussing about that kind of scene. Till date, three characterization tools have been studied widely. Okay, and these are three characterization tools, right? The deep Bruijn graph, matrix algebra, and reachability tree. Here note that these tools are for one-dimensional cellular automata, right? And for two-dimensional cell automata or three-dimensional cell automata, there is no such single tool. There is no such tool to understand the behavior of the CA. Okay, for that we use some parameters, right? But that we are not discussing here. We are discussing the calculation tools, and these are applicable for one-dimensional CAs only. So in my discussion, the CA under consideration, I mean, they are one-dimensional cellular automata. Okay, the first one is deep Bruijn graph. Okay, first one is deep Bruijn graph. So we have studied deep Bruijn graph. We have seen the structure of deep Bruijn graph, and we have studied it while we are discussing the reversibility of one-dimensional cellular automata. So it is obvious that reversibility is one important property, and that can be studied using a graph, right? Using a mathematical structure. So it's a tool. So deep Bruijn graph qualifies as a tool, a characterization tool of one-dimensional cellular automata, right? Although for non-uniform cases, deep Bruijn graphs have been used. However, deep Bruijn graph primarily used to characterize uniform CA, right? Classical CA. That is, all the cells use same rule, and it is also used for finite case as well as for infinite case. However, latter two, matrix algebra and reachability tree, they are particularly developed to study the dynamics of non-uniform cell automata. Since uniform cell automata are special case of non-uniform cell automata. Why? Because if all the cells follow same rule, that becomes uniform CA, classical CA, right? So uniform CA, we can say it's a special case of non-uniform CA, right? So matrix algebra as well as reachability tree, they can deal with uniform CA as well. It's obvious. But particularly these two tools are developed for non-uniform CA. And one more important point, it is developed for finite CA, right? As I was saying that deep Bayesian graph, you can use deep Bayesian graph for finite case as well as infinite case, but matrix algebra and reachability tree, they assume the CA under consideration is finite. Okay, so today we shall start with matrix algebra. In next class, we shall deal with reachability tree. Okay. So matrix algebra is used to characterize linear CAs only. So we use this matrix algebra or linear mathematics to characterize linear cellular automata, and we have defined the meaning of linearity, and we have discussed about a rule. About a theorem which says that CA is linear if and only if each rule of the CA is also linear. That theorem we have proved before. So we are dealing with here only linear CA, and matrix algebra is for that. Okay, so what we need first? First we need, if I want to characterize a CA, a linear CA with matrix algebra, the first and foremost thing is we have to represent a CA by a matrix, right? So next theorem talks about this. Theorem says, suppose let G be global transition function of an n-cell linear CA. Since it is n-cell linear CA, we are talking about finite CA only, you understand? Then there exists an n cross n matrix, square matrix T, such that for any configuration X, right, X in x to the power Z, for x to the power Z, you know the set of all possible configurations. This condition is satisfied y equal to g of x, if and only if y equal to t into x, right? Where y is also a configuration. We call that y is successor of x, right? This is very fundamental theorem which says that instead of representing a CA by a function called G, we can represent it by a matrix called T. Well, in this theorem, you can see that y equal to T into X, right? Here, while we call this X and Y, then configurations are considered as vectors. But it is understood. If it is understood from the context, then we don't use order symbol or vector symbol. We shall try to prove it, step by step. At any point of time, if you have an issue, let me know. First, consider our CA is linear. So G is linear, right? What is the meaning of G is linear? That all the rules of the CA, they are linear. That we have proved before. In my early class, we have proved it, right? So now, come to this proof. Consider the basis vectors. Now see, here, since it is linear CA, therefore, the configuration space is nothing but vector space. So this set of all configurations, S to the power L, forms actually a vector space, right? Forms a vector space. Now, from that one, for any vector space, we know from understanding about matrix algebra linear algebra that any vector space can be generated by a set of vectors, set of independent vectors. We call them basis vectors, right? And here we have considered that E0, E1, En minus 1, they are the basis vectors, right? They are the basis vectors. Okay, so what is the definition of basis vector? Using basis vector, we can get all other vectors of the space. So if you consider, if you can take an arbitrary vector, say x. So x is actually linear combination, a linear combination of these, basis vectors, right? Further assume that g of ei equal to vi. See, just now I have said that ei is a configuration. It's a basis vector. It's okay, but it's again a configuration, right? My vector, my configuration space is a vector space. So each vector is actually a configuration. So ei is also a configuration. So I applied g over that ei, and suppose that is vi. That I have assumed. Okay. So now that I get from the definition, you take any configuration x, that x is actually, I can express x as, say, x0 e0 plus x1 e1 plus x dot 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 plus x n minus 1 e n minus 1. That we get from the definition of basis vector. X vector I have taken, since e0, e1, n minus 1 are the basis vectors, therefore any vector x can be represented a summation of this, this e1 is ei is multiplied by xi, where x is a scalar. In our case, xi always, that belongs to S, is my set of states. What I've considered here my S is 0, 1, 2, 3, d minus 1. So I am considering my system is having d states. Each cell is having d states. So S is actually 0, 1, 2, 3, d minus 1, right? So xi, so these are the scalars, right? So that I can get. So what I'm saying here, that any vector can be expressed in this way. Since here is a vector, since vector is each vector is a configuration. So any configuration can be represented in this way. Maybe. Next query.
Sir, I have a question.
Please. Please.
This we are considering is for a vector space, but is it true for any C, or is it true for only linear C?
Sorry.
No, S to the power L, we are considering that as a vector space, right? Otherwise, you can't take the basis vector.
Yes.
So, so that vector space property, it will be satisfied only for linearity, or it will be, for any arbitrary C, we can consider S to the power L as a vector space.
For any x to the power, say you have to consider as vector space. No.
I'm asking. This is the property of linear C, right?
Right. So in case of linear C, the question of vectors are coming, right? If it is not, then how can you say this one? No.
No. Then, if it is linear CA, then that S to the power L will form a vector space. That also we have to prove somewhere.
That
That also we have to prove. We are considering that If it is linear, then s to the power l, that state space will, configuration space will form a vector space.
Oh, okay. That you have to prove really?
Otherwise, in general, it is not true. Only for linearity, it is true.
Right.
So, I guess it is coming from the property of linear rules, that additivity and homogeneity,
Yeah,
these
yeah.
two properties are satisfied, that means it will become a vector space. But
Right,
do we
right.
need to prove that?
Okay, from those properties, I think we can easily prove that one maybe. But in this
Yeah,
case, I have not yet.
yeah.
This is not here actually. But right, your point is accepted that
Hmm.
since it is for what I am saying it's only for the linear CA. So I'm not considering arbitrary one,
Hmm.
so I should prove it first. Okay, okay, okay. So here I am showing you that how what I have claimed here. I claim that any vector or any configuration in this case we can represent using these basis vectors. Say consider say x is like this. So okay, you consider n equal to 4 and say d equal to 3. I mean say my s, it is like this 0, 1, 2, right? And my configuration x is my configuration. Say consider 0, 2, say 1, 2. Suppose this is my configuration. Now here what I'm doing, say I'm taking say E0, say like this one, say 1, 0, 0, 0. This I'm taking E0. E1 I'm taking 0, 1, 0, 0. If it is so here, so X is my configuration which I want to represent it as vector as a vector. So how can I write it? I can write it 0, 2, 1, 2, right? So this is you understand. I can write it say 0 into E1 plus 2 into E2 plus 1 into E3 plus 2 into oh sorry, it will be 0, it will be 1, it will be 1 into 2 E2, and it will be 2 into E3, right? So that I want to mention there, that if I consider any configuration which is considered as vector, right, which is considered as vector, that can be expressed uh, in this way, right? That can be expressed in this way. So I'm having this E0, E1, E2, E3, and these vectors, these are basis vectors. These vectors are independent, and using these vectors, I can express this x. I have taken x arbitrary. You can take any other x, and you understand that by properly setting the scalar part, you'll be able to get any configuration, right? Okay. Okay. So now what I have written there, I have written that any any config, any vector x is actually, it is actually equal to 0 to n minus 1. So xi dot ei, I can write, right? Note that for any vector space we may have a different sets of basis vectors. It's not that basis vectors are unique. In this example, what I've shown you, for this basis vector, I can represent it, in this way. If you take other another set of basis vectors, same is applicable. On the in the that time x will be different, but that I'm not going that part. In my example, I shall take e0 like this one, e1 like this, etc. This kind of e0 e1 I shall consider. So this is my x. I have taken arbitrary x vector, and this is xi dot ei. I can write it. Now try to find this one, g of x. What will happen? It will be g of summation of I equal to 0 to n minus 1 xi dot ei. Oh, ei, they're the vectors. Okay, so I'm missing to put vector symbols here. Sorry. Yeah, these are vectors. Oh, it's important. So this is equal to what I get here. So G is linear, means it is additive as a homogeneous. So using the additivity rule, what I can do? I can write this one. I can take G inside of the summation 0 n minus 1 G of xi dot ei, right? Now here xi is scalar. So from the homogeneity property of the linear function, I can bring this one ei out of this G. So I can write it like this: xi and dot G of ei, right? Now what is this? This I have assumed as vi. Recall that I have assumed this is the next configuration of ei, configuration ei. This is vi. So that I have assumed this is vi, right? So here what I get like this: I equal to 0 n minus 1 xi into vi, right? Vector vi. So vi is a vector, so I can expand also vi. Okay. Let us expand this vi. So represents vi in this format. So how can I write? So I'm writing set v0i v1i dot v n minus 1 I transpose. Okay, so I'm taking transpose of this because we represent it as it as a column vector, right? That we get. So this is actually is equal to x will start from 0. I will start from 0, then 1, then n minus 1, right? Okay, go back to my presentation window. Then what I get? I get this one. This I get that g of x is equal to x0. So just I have expanded, that one x0 v00 v10 dot vn minus 10, right? In this way, and v x1 into v01 v11 then Vn minus 1, 1, and transpose T. All the cases transpose T is given. Now, this relation can also be represented in this way. Okay, you can check it. So some step jumps you may find here that this one, the above one, can be represented in this format, in this way. So we get a matrix, n by n matrix, a square matrix, into that x0, x1, xn minus 1. What is this x0, x1, xn, n minus 1? That is my, the configuration x or the vector x. So let us consider the left hand side, the matrix, as T matrix. So let us name it as T. Okay. And so I get G of x vector is equal to T of x, T into x, right? That we get. So what does it imply? It implies that G of x, actually we get a y. Here I have written to make it consistent with the statement of theorem that that if y is the next configuration, then T into x is the next configuration. That is just I'm expanding. So G of x equal to T into x, right? So that I have just expanded here, and that completes the proof, right? So y equal to G of x, even only if for some matrix T, y equal to T into x, right? This is the proof. Okay. I think what Kamalika was talking about, that I have not thought to show you that S to the power L also forms a vector space. That is also what she has mentioned. Also, that is true that we can do it from that one. From that theorem also. Okay. And from property of this linearity, we can do that one. Should I do now? Kamalika, are you here?
Yes.
So I was thinking that yeah, it can be the property of vector space that is also maintained. We can show it. So okay, because if I drop this flow, then if I start proving, then it will take more time. So so you do it. So let me put it as home task, that show that set of configurations S to the power L, right? It forms a vector space when G is a linear CA, right? Okay. 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 So now here issue is how can we find this T?
Sir?
Yes. Yes, please.
Sir, so basically E1 to En minus 1, this is the configuration of a C.
Right. We have basis vectors
that
as well as
that is
configurations. Right. The configurations.
Each of them are configurations, right?
Yeah.
okay.
Yes. No. What is the point?
No, E0 to En minus 1, this basis vector, each of them are configurations of a CA.
Yes. Each of them is configuration.
Yeah.
Hmm. Now here, Shupti, Shupti, I didn't get your point. Is this the only question?
Yes,
Okay. So I in the example
yes, sir.
mm,
Uh,
in the example also I have shown you that
uh,
say one all zero, zero one all zero.
hmm.
You can consider these are configurations, so it will be considered as basis vectors here.
So individually E0, E1, they are
Yeah,
configurations, right?
yes, and they're independent. I mean, yeah, not equal to DJ.
Okay,
Hmm, right.
okay, okay.
Now here the point
Hmm.
is, our the next point is here that so this theorem in the proof we have shown that there exists a t, but how can you get this t? When a c is given, you know that g is not given. Okay, ca is a quadruple. Local rule is given, right? In the ca definition, what we do, what we give, we give the we specify the lattice, right? State, neighborhood, the rule or rules, set of rules, and the rule vector, but not the g. So when rules are given, question is from those rules, how can we get this the t, right? Okay, how can we get this t? So I can give you some intuitive idea here. So first give me you this intuitive idea. Just go to the Jamboard first. This E0 E1, this E0, this E0 E1, if I take E0 E1 E2 E3 in this way, then we'll get some idea how can we get you know uh, 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 the matrix from the local rule. Okay, so 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 let me give one example that, see, I'm taking say E1 is like this. So E1, so E1 is say first 0, then 1, then 0, 0. There are then by many zeros say, right? Now this is a vector. Again 0, 1. This is a configuration also. 0, 1, 0, 0 is a configuration of size n, right? Now if I apply, sorry, anybody is there? Anyone? Oh, let's go Jamboard. it has gone. Okay, I was writing. You have to write.
Sir, it was frame number 20.
It is really so. Oh, thank you. What happened? Hmm. So then,
Previous frame, sir. Previous frame.
to go in reverse direction. Okay. So now, let us consider the ECA rules, right? So ECA rules means a cell depends on its left neighbor as well as right neighbor. Now, if I apply G of this one, if I want to find G of E1, right, then what I'll have? So, what I'll get? Say only this one will affect this cell or that cell, because we are assuming a thing about CA, right? It depends on left neighbor as well as right neighbor only. So on the next finding, if I find the next configuration only, then effect of this one cannot have an impact on these cells, right? It's obvious. So, and suppose this is actually, so what I've considered, this is actually my V1. So in V1, what I can have? So V1, if I write V1 in this way, then V1, V01, then V0, sorry, V00, 01, 02, and etc. V0 in minus 1, right? So, so what does it mean here? That you see here, only these can be, you know, non-zero value, but rest part will always be zero. Why? Because the linear CA. If a rule is R is linear, 0, 0, 0 is always 0, right? If you for any linear rule R, you can check it, that we get from the additivity rule and additivity rule. If you take 0 as the argument of any rule, a linear rule, it will always be 0. So since it is linear CF, so this part will remain 0, all 0. I have written here V0, 2, etc., etc. But sorry, I have written here again, so wrong way. It will be 0, then 1, then 2, then n minus 1 here, and it is 1. It will be 1, 1, 1, and 1. Okay, this convention I was following. Anyway, the point is here, this part will remain 0. and these parts only can be non-zero. Why? That depends on the neighbor dependency. And it gives a hint that by exploring neighbor dependency, I can get this T matrix. And if I want to multiply this with T, say T into say E1, right? Then also I should get this V1. Here I use G, so I get V1. So similarly, similar fashion, if I multiply this T and E1, then I should get V1. So in the T matrix, so somehow these parts are to be 0, and this part may be non-zero value. Okay. So considering this fact, what I get here, say, suppose Ri is my rule of this format. Okay, I have written in general format. So Ri, it x Ri minus x minus Ri to x0 x Ri, and this is my say rule. Okay, so here ai0 aij, they are the constants. I mean, they're the scalars, right? So then the T matrix will look like this one, right? And you can check that with this T matrix, the other properties are followed. The properties, we have said in the proof, these are followed. So and here we call this T matrix as characteristic matrix. So this, both the names are used generally. I mean, in literature, this matrix is also called T matrix, but its name is characteristic matrix. Take an example to be clear. So consider the CA 4 cell CA 90, 150, 90, 150, right? So in this case, how T matrix will look like? So I can write here Tij equal to 1 if I depends on cell j, 0 otherwise. That I'm saying. That how I'm getting so? See, that I'm getting from that from the above matrix representation, right? So okay, and now if it is so, then for this on a null boundary condition, for this given T matrix, for given this CA, I can get this T matrix. Now go to Jamboard again, because I have to tell a few more things. What is Jamboard again? So what I have taken? I have taken CA as 90, 150, 90, 150, right? Now here 90 rule 90, it has 3 arguments. So if I consider x, y, z, right? Okay, I should say x, y, z, or what I have said there in the mat, what I have said, it is x0, yeah. So I should not say x, make it consistent. I should say it here, x minus 1, x0, x1. Why? Because here r equal to 1, right? And so following this format, I get this one. And this is my binary CS, so s equal to 0 1, right? So this is my rule 90. We have discussed it. 90 is left neighbor this plus this mod 2 that we have discussed in previous class. So actually this is minus 1 plus x1. Mod 2 is there. I'm not writing mod 2. Mod 2 is always applicable. So is actually what I get 1 into x minus 1 plus 0 into x0 plus 1 into x1. In case of 150, I get it x minus 1, x0, x1. Right. Here, what I get x minus 1 plus x 0 plus x1. Why it is so? Because we know we have discussed in last class that previous class maybe that 150 it is actually XOR of these three, right? So it is 1. I can write it actually 1 into x minus 1 plus 1 into x0 plus 1 into x1. Now what is my style here is, see, first rule is rule 90. What rule 90 says? The cell x0 means cells are under consideration, minus 1 means left, plus 1 means this is right one. There is cell 0 depends on left neighbor, in this case left neighbor, and right neighbor because it is 0. Okay. So anyway, so I shall use this one actually. Here I get this triplet 1 0 this 0. This part in this diagonal part, so here it is 0. This 0 I am writing. See here I shall, okay, let me use a different color. Okay. Here is 0. This x is 0. So I am putting here 0. Right? Because it is in my old format, it was A00. Right? The first cell. Right? So now it is dependent on left neighbor because it is 1 is there. But where put I 1? I have considered null boundary case. So if it's null boundary case, so it's the boundary cell, so there is none, so don't worry. Now this is the one, and what is this? This is actually what I shall write here. I shall write this one, 1. Okay, and here, so this is done. This is for the first cell, this one. This is for first cell. Now come to the second cell. In second cell, it tells rule 50, 150. It depends on here. This is the this one. Here 1, 1, and 1 is 1. Self dependence is there, as well as left as well as right. So here, what I write here in the diagonal wise, it is 1. This one for this one. Then it has dependence on left one, right? So I put here right, left one as well as right. Here 1, so I put here 1. So next rule is 90. In case of 90, the same, x0, it is 0, middle one is 0, this is 0, this is 0, this is, so 1, left side it is 1, right side it is 1. Last one is 150. So in 150, in case the self is always here, it is 1, but it is also left is 1 that I am written. But since it is null boundary condition, this is the end of the cell. This is null boundary condition. So in the right hand side of this one, there is nobody. No cell is there. So we needed to worry. So this is the structure you can see. So what I put in each individual row, what I put actually this value of the constants. Here 1, comma 0, comma 1. Here is 1, comma 1, comma 1. So if you take any linear rule, and if you then for the linear rule you can express them in this fashion, right? If you have the 2r plus 1 number of argument, right, then what will have? Then 2r plus 1 x size will be you'll have, and then you'll get some scalars. You put the scalars in this fashion, okay, then you will get the T matrix. And for the rest are all 0. It's a sparse matrix. T matrix is a sparse matrix. So in this way actually, no, recall that what I have written here in that case, that if you have that for cell I, okay, let me remove that I. Okay, just R I am writing. So R is linear rule. So of radius small r. Then how it look like? So it will have x minus r, then x minus r plus 1 dot x0 x r, right? Is the argument. So then what will have here? So here, I'm just writing here like a minus r into x minus r plus a minus r plus 1 into x minus r plus 1 in this way, plus a0 x0 plus dot plus er xr. So what matters? This constant matters. The scalar values, they matter. So what I put here, this a0, this value put in the it is diagonal element. These elements are considered as diagonal element of the matrix. Now if it is the ith cell, suppose this is the ith row, so then a0 will correspond to this one only. So then left side will be in left part and right side in right part. That I have written in that one. Now if you are happy with binary C only, then so this matrix will be binary matrix, will having value 0 and 1 only. Now one means I can interpret it in this way, that a cell depends on that cell, right? So diagonal elements, so this is my interpretation. I am saying TII, I'm interpreting it, it denotes whether cell I depends on itself. Here it is 1 means it depends on itself. You can see it's 150, it is 1. Here it is, you can find x0. It depends on itself. Whereas in case of 90, it does not depend on itself. It is 0. So I am interpreting. So TII means it depends on cell I, on itself. And if I write here, say if I write here, say Ti I plus 1, it says whether cell I depends on I plus 1 or not. If it is 1, then depends on, otherwise not. Right? Right? In this way, I know, we can interpret this one. So T matrix is also called as dependency matrix. Dependency matrix, right? It is also called as dependency matrix. You can see one interesting property also here, okay. This matrix is symmetric. Say Tij, okay. If cell I depends on J, yeah, Tij is equal to Tji. Means if a cell I depends on J, it implies cell J also depends on I. Right? This is always true. So therefore, in this matrix, okay, oh, sorry, this is not true always. Sorry. This is not true. In case of, this is true for uniform C only. So no, in general, it's not true. Sorry. So okay. So anyway, so so in this way we can get this T. Any question after this? Yes.
Sir?
Yes,
Sir?
please.
Sir, the blank spaces will be filled by 0.
Yeah, 0.
Will the blank spaces filled by 0 or okay? And sir, what is the significance of forming this kind of matrix? I mean, why we are using this matrix?
Why you are using?
Why do we form such matrix? I mean, why do we form such matrix? What is the significance of the matrix?
No, this matrix can generate all the elements, the vector space. This matrix can generate the vector space. Right. This matrix. So what we have proved first?
So by looking at the matrix, we can only
By looking at the matrix?
that T is linear.
No, since
By looking at the matrix, we can understand what the rules are in the non-uniform C.
that you can understand, or in the converse way, you can say that if you know the rule vector, then you can form that, that matrix.
Why we are forming this matrix?
Sorry, why?
Why we are forming this matrix?
No, first we have what we have shown first. So if CA is linear, for that linear CA, you can have a matrix, that we have. There is some matrix. Okay, there is some square matrix. Okay, here I am telling you this is one way. This is the way of getting the matrix from rule. Right. I can show you what is the advantage of this matrix.
Sir, one more point actually.
Yes.
In this matrix,
Just wanted to know that.
Please, yes.
Yes, sir. Well, one more point is that using this matrix, actually, we can find the equivalency also. Equivalency of cycle structure is equivalent. That means we can swap the rows and columns, and by that we can change the rules, but the cycle structure remains same.
What is that? That we have not covered yet.
Uh,
No.
okay,
Uh,
sorry,
and
sir.
the point is not clear to
What I
me.
try to say,
By that by
yes. What I tried to say actually, suppose the rule vector is like that 90, 150, 90, 150, again 90, 150, 90, 150. So we can change the rule 90 to some other rules like 240, or you can understand, sir, right independent or left independent. And by only in case of matrix, actually we can do some matrix operations like swapping operation, like row operation or column operation. By that we can change the, so in the using matrix representation, we can easily find the equivalent in respect to cycle, number of cycles or cycle structure.
what does it mean by you easily? Are you talking about complexity? Easily means it's possible, and it's the way of finding out this what you're saying, equivalency, etc.
Yes,
No,
sir. Actually,
yeah.
yes,
Sukarna,
Kamalika.
Sukarna, you continue.
Now, actually, what I try to say, sir, by some row matrix operation, we can do that. That means if the
Right.
CA
Right.
is non-linear, it is difficult for us to find out the corresponding, uh, according to my point of view, that is equivalency. Equivalency means cycle structures.
Possible. In case of linear C, it is simpler than nonlinear C. Much, I mean, very simple compared to nonlinear C. If you want to find, say, in your word equivalency,
Yes.
possible to find. Yeah, and so it is so popular. Once you are in the domain of matrix, now then you use the
Yes.
standard results of matrix algebra.
Yes. Yes. That I
Why
tried
it
to
was
say.
so
Using the
popular? Oh. Once you are able to represent the CA in terms of matrix, then CA is immaterial in some sense. Okay, background you're running CA, that's a different issue. But now you are dealing with only the matrices. That's all. Yes.
Sir, sir, you said that Tij is not generally equals to Tji, but this matrix will always be symmetric matrix, right? Then why it will not be equal?
Why do symmetric matrix?
It is supposed to be symmetric matrix.
Uh, okay. So just let me use a different color. I'm just a trivial example. Suppose here you use, can you see this 91, 150, 90, 150? Suppose here you use the rule 0, 90,
Okay.
0, 90, 150. Then 90, it will be the for 90,
Yeah.
right?
Hmm.
Then what it will be for? So here will be 0, means all 0. What is 0? 0 means always 0. So 0, 0, 0. So it
Hmm.
will be 0, right? It will be 0. Am I right?
Yeah.
So then this differs this
Yeah.
this position.
Okay. So only for uniform CA this is symmetric. Otherwise, it is not symmetric.
No, there are other CAs they are symmetric, for but in general I'm saying.
Okay.
I'm not saying general it's symmetric.
Okay. Okay. Thank you.
Or and Shukruti, you were asking your question was
Actually,
what is the
I was
rationale of getting this
asking the
one? No?
benefits of. Sorry, sir.
Benefits of matrix. Benefits of matrix.
Yeah, yes,
So lots of benefits.
of
What are
this
now?
matrix, forming this, where we are, where do we use this matrix?
No. Once you have, once you'll be able to represent a CA by matrix, as I was saying, that you can deal with the matrix only. In matrix algebra, there are many standard results that you know that you can apply here. Hmm. And linear mathematics, it has several advantages. By mathematics, we generally mean the linear mathematics. If you want to have flavor of mathematics, the mathematical results, they all are almost all are linear mathematics. So that result, that advantage you can get.
So by
Yes.
so by non-linear rules also can we get such
No,
matrix?
no. This is only for linear.
By
This is
because we get such dependency of
right.
vector.
This is only for linear C. It's only for linear C. And one thing, mm, one intuitive idea why I'm doing so, you can get from the basis vectors, right? In this matrix, if you multiply with some basis vectors, say all 1 and 0, what will get? So only, I'm giving the counter intuitive argument. So why I concentrate on only this rule and local neighborhood, etc. See, using multiplying this matrix with this basis vectors e0, e1, etc., where you have only one single one and all 0. So in the resultant, almost all will be, non-zero. Sorry, 0. Only that particular cell and R in upper side on R in lower side, these much positions may be non-zero. Right? That idea also you can get, and here you can see that all the powers are non-zero, zero. In this matrix, what you can get, I don't know whether I'm clear or not. See, all are part are 0. Okay, you do it and see that the property of the theorem in the proof steps of the proof that is maintained here. Achha. So next is this for null boundary condition. It has some dependency on boundary condition. In case of periodic boundary condition, you can see. So the example I have shown here, it will be a bit different. A little bit different. Oh, sorry. Just see, this is for the null boundary case. Just I am telling you, if I want to develop it for periodic boundary case for the same CA. The same CA. So my CA was CA was 90, 150, 90, 150 and periodic boundary condition. So in this case, how it look like? 0, 1 as usual, 1, 1, 1, right? And here it will be 1, 0, 1 and 1, 1. It was for that we have done in case of null boundary case. It is rule 90. 90 has dependence on left left neighbor, but since it is null boundary condition, so we have ignored this part. But if it is periodic boundary condition, then what will happen? So its left neighbor is this one, right? Because you can find this kind of thing. So it will be 1, right? So this part will be 1. Similarly, for the last cell, 150, it depends on left as well as right. But in case of right, what is the next cell? What is the rightmost right cell of the rightmost cell? This one, because it forms a circularity. So therefore, it is 1. Okay. So then rest part is 0. So rest part is 0. So important thing is here. So these two positions of the T matrix. So in this way. So you can generalize it. This is for article 2.1 I have taken. So you can generalize for any R, right? The same logic. Now, what I claimed, that by using this T also, G of X equal to T of X actually. So I can evolve the CA using this T, right? So let us take an example. Let us evolve this one by T. So evolution of this CA 9150 9150 with null boundary condition. So this is my CA. How can I evolve? Now once you get this T, you need not to actually this T is a different form of representing G, you understand. So you need not to consider the rules, other things. So this T is sufficient. Okay, to evolve a CA. So here, this is my T. Now you take any configuration. Yeah, here you note that if you take all zero as your initial configuration, means 0 0 0 0, what will happen? T into 0 is always 0. So in linear CA, from 0 you always move to all 0, right? However, if you take initial configuration as 0 0 0 1, what will have? So it is T into 0 0 0 1. You can check it. Multiply. If you multiply this capital T with this column vector 0 0 0 1, you'll get 0 0 1 1, right? Okay. Now, if you want to further get, say 0 0, if you want to find out the next configuration of 0 0 1 1, then again T into 0 0 1 1, then you get the next configuration. From the next, you can get again you apply, if you multiply that configuration with T next configuration in this way. So you'll get the transition of configuration, and it will look like this. Recall that we have seen this in this diagram. If you can recall, we have taken this C as example, and we have observed this transition diagram. So same you can get using T also, right? Same you can get using this T also. Here interesting point is, one more interesting point is, suppose you want to find out a configuration after say 8th time step, right? What you do? What you normally do in case of if you know only G, say then G, then G2, G2 G of X, then G of X to G of X. In this way, we move from one configuration to another configuration. In this case, you can simplify this in this way. So suppose here what we have get, say this is T of say say uh, 0 0 0 1. You got what you got? 0 0 1 1, right? Now, so similarly, now using t into 0 0 1 1, you'll get other. Okay, so what is that? Let me write it down. It will be 0 1 1 0. It will be 0 1 1 0. So it will be 0 1 1 0.
Sir, you are considering null boundary or periodic boundary?
Oh, here I am considering null boundary. Sorry. Here I am considering null boundary condition. Yeah. So null boundary. Although this side by side. So I have considered null boundary. So that I can get. So now what I get here, if you know, so what I get actually t of t into is actually that I have received here 0 1 1 0. This actually t square of 0 0 0 1 is actually 0 1 1 0. What I want to say that if you somehow can find out this t square, you can jump this configuration. You need not to face this 0 0 1 configuration. So you know 0 0 0 0 0 0 1 initial configuration. From this initial configuration, you can directly move to 0 1 1 0 as if you are jumping. Practically, I mean, this jump is incorporated in the t square, finding of t square. But what I want to point out here, if you somehow know the value of t, know the matrix t square, by multiplying this, you can directly go to that particular configuration. In general, so say to the power k of say into x. Here, if you can know to the power k, so from this x, you can move to a configuration after a configuration which is reachable after k time steps, right? So this kind of jumping possible if you somehow come to compute these values t square, t cube, t4, etc. Right? This is also possible here. So this is about matrix representation of a linear CA. As I have said, that once you have represented in matrix form, you can use the standard standard results of matrix algebra to characterize your linear cellular automata. Okay, right. There is one interesting thing. That is, this matrix algebra was developed only for linear CA. The theorem which you have stated here in this class, that is only for linear CA. However, this tool can be extended to a new, non-linear CA, very close to non-linear CA, which is named as, complemented CA. Please recall what is a complemented CA. In a rule vector, if the rules are either linear rule or complement of any linear rule is used, then the CA is called complemented CA. What is the complement? In a logical sense, I am saying complement, right? In the digital logic, if you have a rule is a function, it's complement function, you just put a bar, right? That is a complement, right? I'm talking about that rule, right? So a rule is complemented rule if we get that rule by complementing some linear rule. That's called complemented rule. And in the rule vector, if the rules are all are, at least one is complemented rule and the rest are linear rules. Okay, then the CA is called complemented CA. So truly, strictly speaking, that CA is not linear. Hence, the CA is non-linear. However, it's very close to linear CA. Okay, so this CA can also be characterized by matrix algebra. Better to say some extension of matrix algebra. For that, we need an inversion vector. What is inversion vector? Inversion vector is, in inversion vector we write it F. See Fi, so if there is n cell CA, so F0, F1, F2, Fn minus 1. So if F0 or if any Fi actually uses complemented rule, then in the F vector content is 1, otherwise it is 0. Okay, take an example. Says consider this four cell complementary CA 90, 150, 165, 150. 90 and 150, both the rules are linear rules, but 165 is complemented rule. Okay, should I clarify why it's complemented rule? Okay, let me clarify. So 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. In case of rule, the rule 90. Rule 90, it is 0, it is 1, it is 0, it is 1, it is 1, it is 0, it is 1, it is 0. It's rule 90. It is rule 90, you can check it is rule 90. And this is a linear rule. This is a linear rule. Now, what I'm saying, okay, linear rule is, see, I'm defining a new rule. I'm finding a new rule where, see, 90 x, y, z, I shall take all of this complement, right? And this is some rule for some x, y, z. I don't know what rule I'll get. Just let's check. Suppose rule name is R. So R x, y, z is say is equal to 90's complement always. So how can I find this one? Say 0, it is 0, so its complement is 1. It is 1, this complement is 0. It is 0, it is 1. It is 1, it is 0. It is 1, it is 0. It is 1. It is 0. It is 1. So I get a new sequence, a new 8-bit sequence. The second rule, what is this? Is 128 plus it is 128 plus 32. This is 32 plus this is 2 4 plus 1, right? This is 165. So rule 165, it is a complemented rule. We are talking about these rules which are complement of some complement of some linear rule, right? So 165 is a complementary rule. So what I have taken is the rule vector. So 90, 150, then 165, then 90, right? No, it was then 150 I have taken my example. Yeah. Right. So this is the complementary rule. So this CA, the CA rule represented CA defined by this rule vector. This is complementary CA. This is complementary CA. Right. Now I'm saying that my matrix algebra can be used to characterize this kind of CA also. How will do that? How do I? Acha. In case of complementary CA, we restrict ourselves only on the binary cases, right? So all for linear CA, what I have considered that so S is 0, 1 to D, so distant CA I have considered, but here we are talking about only binary CA, right? So we are not moving away from this binary case, right? So what is the way? So when the rule vector is given like this, when a rule vector is given like this, I first find out the linear counterpart of the CA. What is its linear counterpart? Its linear counterpart is this. This is this one, 150. So then what I say that so when I get this linear CA, I can use T matrix. I can get T matrix for the CA, and that we have already done. We have some T matrix. Along with that, I need a F vector. In this CA, what will be my F vector? F vector will be, so first cell is not the inversion, it's linear rule. This is not the inversion. Directly I am using linear rule. Is okay. This is inversion of the linear rule. Okay, so it's 1, and this is linear rule. So this is my F vector. Now, how can I get the dynamical behavior? Just today I am showing you that using this T matrix and this F vector, I can evolve. I can get the next configurations of the CA. I mean, evolution is possible. I can trace the evolution. How? Say again, take say my configuration is X. My configuration is X, and this is 0, 0, 0, 1. The previous case I have taken. And so how can I get its next configuration? It's like this one. So T into X plus F. Right? T into X plus F. Right? So by doing so, I can get the next configuration. Nothing else. So consider this X. So let's see. So T was, in this case, T was 0, 1, 0. Yeah, null boundary condition I am considering, right? So I'm considering null boundary condition. So 1, 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1. This is my T for this matrix into X. X is X is 0, 0, 0, 1. And what is F? This F is this is the one. This is my F. It is 0, 0, 1, 0. So in this way, I can get the next configuration. Okay. Now what is this? This is, if we multiply, then you'll get this was hopefully so 0, 0, 1, 1 plus 0, 0, 1, 0. Right? So okay, from this one, what I can get? So 0, 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 1 is 0, right? And 1 plus 0 is 1. This one. Okay. Okay.
Sir?
Yes. Please.
Sir?
Yes, please.
Sir, in case of three or more state Cs, all the operations will be done under mod D condition, right?
Right. Good question. And always under modification means, see, when we talk about vector space now, then we have to consider some underlying field. Right. That part, I have not mentioned, in fact. So underlying field you have to consider. You have to consider. So here, so addition or all additions, multiplications, the operations on that field, right? In this case, our field is Gauss field 2, GF2. Okay. So in Gauss field operation, it is always
Yes,
one.
for binary Cs.
Uh, it is GF2CA because this field is GF2 I am mentioning here. It's linear. If it is binary, then by linear you can say it is GF2. Okay. Then 1 plus 1 well is XOR operation. It's mod 2 operation, and or yeah, it's mod 2 operation, and in field also in GF2 also 1 plus 1 is 0, right? In the in the class table,
Yes.
plus is the operator no? Here plus is an in operator. So for that you need to have operator is a function. You need a table. So in the table you will always find the 1 plus 1 is 0. So if you consider it is F2, so there is no question of putting mod 2. But if you look at the history, how this Gauss field theory developed, then these all are developed from modular mathematics. So if we go back to the origin, so then you can say mod 2 version is there, right? So here, in the previous case, from 001, 0001, we go to 0011, but here from 001, 0001, I am getting again 0001. Yeah, you can see you have started from 0001, and again you have get 0001. Same, same configuration you get back. So it forms a self loop, right? From 00 for this cell for this year, from 0001 you will get from 0001, right? However, that is not written here. Just I'm telling you, if you consider this, sorry, if you consider this CA, and if you one by one export the all configurations, you'll find that it is again like before maximal length cell automata means 0001 is for the single cycle, no problem, but the rest configurations will form a single cycle. So some theory is there, there's some background theories there. I know that is not, we shall not discuss it here. But there are some cases where this transition diagram of this one linear CA and its complementary CA received from the linear CA, they may vary, right? And in many cases they don't vary, but some cases they vary. So that's an interesting point. Okay. So here what I want to point out that matrix algebra can also be extended to understand the behavior of a special type of non-linear CA called complementary CA. It's very interesting. So you can characterize them using linear CA, and they share linear CA and complementary CA. They share many common properties. Okay, we shall see reversibility. Say a reversible CA, if a linear CA is reversible, then it's that part is also reversible. That we shall see. I hope we'll prove this theorem in coming classes. So they share many common properties. So the point is what I tried to say: matrix algebra for linear C is a good characterization tool, and that can be extended to this class of CS. Okay, and that's all. Any question? As usual, boundary condition have a great impact. Here also, you can see these things we have done for. We did these things for null boundary condition. If you consider boundary, periodic boundary condition, this behavior will get changed, right?